This is the New York State Regents Physics Course. Topic 8 is current electricity. This section, 8.5b, is about calculating resistance in series and parallel circuits. Before we can discuss how to calculate resistance, we have to decide whether we're dealing with a series circuit or a parallel circuit, because some of the ways to calculate resistance depend upon whether it is a series circuit or a parallel circuit. So here we have a series circuit, and you see that a series circuit has only one path for the electrons to follow. The electrons have no choices about which way to go. Let's say we have a current here of 3 amps. That would be 3 coulombs, 3 coulombs per second. Every coulomb, all the electrons follow the same path. There are no choices about which way to go. All the electrons follow the same path in a series circuit. Now, looking at the parallel circuit. In a parallel circuit, we have points called junctions or nodes. Here is the first junction or node. At this point, when the electrons get to here, they can either go this way, following this path, or they can go this way, following this path. And technically, we call these paths branches. All right, so this this coulomb of electrons can go this way, all right? And this coulomb of electrons can go this way. This coulomb, I don't know which way it's going to go. Maybe it's going to go that way. Maybe it's going to go this way. It depends upon the resistance of each of these resistors. But again, when the electrons get to here, they have a choice. There's more than one path, more than one branch. When the electrons get to the junction, they can either go this way or they can go this way. You could also draw it like this. They can either follow this path or they can follow this path here. All right, so in a parallel circuit, there is more than one path. The electrons have choices. All right, now, just very quickly, the definition of a junction or node: a point in a parallel circuit where the current, that's the electrons, the flow of electrons, splits. At this time, I'd like you to make sure that you have a copy of a chart that shows the different equations for calculating total current, total voltage, and total resistance for series circuits and parallel circuits. Now, I'm going to display the chart in just a moment, but if you'd like to download a copy for yourself, go to this website, nysedregents.org, click on Reference Tables, and somewhere down in the reference tables, you'll see the 2006 edition of the Physics Reference Tables, where you will find a copy of this chart. We have said that in a series circuit, all the currents are equal. That means that the equation for calculating total current in a series circuit is going to look like this. The current total is equal to the current through the first resistor, which is equal to the current through the second resistor or component, which is equal to the current through the third resistor, etc., etc., etc. Now, on this circuit, we could call this R1, the first resistor, and we could call this R2, the second resistor. Now, for a parallel circuit, the total current, remember that the currents are not all the same. The total current is going to be equal to the sum of all the other currents in the circuit. So if this is R1 and this is R2, the current through the first resistor would be I1, and you would add to that the current for each other resistor in the circuit. I1, I2. If there is an I3, an I4, an I5, they would be over here. All right, dot, dot, dot. There might be an I4, an I5. You just add up all the currents to get the total current in a parallel circuit. Again, look and see what's equal in a series circuit are the currents. In a parallel circuit, you add them up. How is a series circuit different from a parallel circuit in terms of calculating the total voltage? Well, in a series circuit, you add up all the voltages to get the total voltages. So, the total voltage, V total, would be equal to V1 plus V2 plus any other V's that are in the series circuit. Now, V1 in this case would be the voltage of the first resistor. V2 would be the voltage of the second resistor. If there was a third resistor or a light bulb, whatever, then there would be a third voltage, a fourth voltage, a fifth voltage. You add up all the other voltages to get the total voltage, which would be the voltage of the battery. Now, in a parallel circuit, all the voltages are the same. That means that the total voltage, which is the voltage of the battery, right, would be equal to the voltage of the first resistor, which would be equal to the voltage of the second resistor. And if there is a third resistor, a fourth resistor, a light bulb, whatever, that would be your higher numbers here. And you would add, they would all be equal. All right, so in a parallel circuit, all the voltages are the same. The total voltage is the same as every other voltage in each branch. Now, for a series circuit, you add them up. You add them up to get the total voltage. Now, on to the topic of this video. How to calculate the total resistance in a series versus a parallel circuit. In a series circuit, it's really, really simple. You just add them up. So, for example, right, the total resistance of this circuit would be R1 plus R2. Now, if there were other resistors or light bulbs, whatever, then there would be an R3, an R4, and R5. So again, for a series circuit, you just add up the individual resistances, and that's going to give you the total resistance. R1 plus R2, in this case, would be equal to R total. Now, parallel circuit to calculate the resistance is probably one of the trickiest equations in all of your first year algebra-based physics course. You got to be really, really, really careful. It's very easy to make mistakes. The algebra isn't difficult, but there's lots of points at which you can make a mistake. So we're going to go through this very, very carefully in this video so that you see how to do it without falling into those little traps. Now, for a parallel circuit, the total resistance, now you're not going to calculate the total resistance directly right away. You're going to calculate the inverse of the total resistance. And it's going to be equal to 1 over R1, the inverse of the first resistance, plus the inverse of the second resistance, etc., etc. All right, and there could be more resistors. In this case, there's only 2, so you would chop this equation off right here, and you would only use this part, obviously. All right, so this equation is super, super tricky. All right, it's not really difficult, but there's a lot of places where you can make mistakes. All right, so let's do some problems. First, we'll calculate the total resistance in some series circuits, and then we'll calculate the total resistance in some parallel circuits. Now let's look at the difference between adding up the total resistance for a series circuit and adding up the total resistance for a parallel circuit with identical components. So, we have here a series circuit consisting of a 12-volt battery and 3 4-ohm resistors. So this resistance is 4 ohms. This resistance is 4 ohms. And this resistance is 4 ohms. All right, all of the resistors are the same. Now, what we'll do after that is the same 12-volt battery with 3 identical 4-ohm resistors. So R1 would be 4 ohms. All right, R2 would be 4 ohms. We'll put it down there. And R3 would be 4 ohms. All right, so here we go. The total resistance, all right, R total for a series circuit is going to be R1 plus R2 plus R3. You add up all of the resistors. There are 3 resistors here, so it's R1, R2, and R3. All right, so now let's start plugging in. R total equals R1 is 4 ohms. R2 is 4 ohms. R3 is also 4 ohms. Add them all up, and what we get is a total resistance of 12 ohms. All right, we have a total resistance here of 12 ohms. Now, please note that the total resistance is greater than any one single resistor. You add them all up to get the total. All right, now let's look at adding up the total resistance for a parallel circuit. The equation, 1 over R total equals, now remember, R total, some people like to call it the equivalent resistor, the equivalent resistance, REQ. So whether you call it the equivalent resistance or the total resistance, doesn't really matter, all right? It means the total resistance. Now, we've got 1 over R1 plus 1 over R2 plus 1 over R3. All right, so let's start plugging in. All right, 1 over R total equals 1 over 4 plus 1 over 4. Oops, forgetting my significant figures there. Plus 1 over 4. And in terms of significant figures, this is 2 significant figures, so let's get rid of that 0 there. Okay, this is 12 ohms. Just correct that. All right, so we've got here 1 divided by 4 is 0.25, plus another 0.25, plus another 0.25. Add those all up, and we find that 1 over R total is equal to 0.75. So if you add up this plus this plus this, you get 0.75. Now, I don't want 1 over R total, I want R total. Now keep in mind that because 0.75 is really over 1, all right, the R total and the 0.75 are inverses, you can just switch them. All right, so let me erase over here, and we'll pull this up to here so that we can complete this problem. Remember I said it's a little harder to calculate the total resistance for a parallel circuit than it is to calculate the total resistance for a series circuit. So we know that 1 over R total is equal to 0.75. Now, you can just switch these two. All right, 1 divided by 0.75 is equal to R total. All right, so R total would be 1 divided by 0.75. Do that on your calculator. All right, 1 divided by 0.75 is going to be 1.33 repeating ohms. So the total resistance of this whole parallel circuit is only 1.33 ohms. And what you notice is that when you calculate the total resistance of a parallel circuit, the total resistance is going to be smaller than the smallest single resistor. Now these are all the same, they're all 4 ohms. So the bottom line is the total resistance must be less than 4 ohms. Now, I just want to show you, if you don't like switching the inverses there, you could cross multiply instead. All right, knowing that here, all right, 1 over R total equals 0.75. You know that the 0.75 is really over 1, so you could cross multiply here and say that 1 equals 0.75 R total. Now divide both sides by 0.75. You're going to get the same math as we just did. Those cancel, and R total again is 1 divided by 0.75. R total is going to be 1.33, repeating, all right, ohms. Now, since we were given the total voltage, which is the battery or power supply, and we just calculated the total resistance, it's a simple matter at this point to calculate the total current for each circuit. So let's do that. All right, we know that the total voltage, the battery, for the series circuit is 12 volts. We know that the total resistance is 12 ohms. So we're going to try to calculate the total current. Now you know that Ohm's law says R equals V over I. So we're going to, since we're trying to find I, we're going to switch the inverses and put I equals V over R. So here we go with the correct equation. I equals V over R. Now, keep in mind, when you use Ohm's law, you should always put all identical subscripts. So if we're trying to find I total, we should use V total over R total. Whenever you use Ohm's law, make sure all of the subscripts are identical. So we take V total, which is 12 volts. We divide by R total, which is 12 ohms. So we're going to find that the total current, 12 divided by 12, is 1 amp. All right, the total current for this circuit is 1 amp. Now, over here, the parallel circuit is going to be simple. It's going to be exactly the same format. We know that the total voltage of the battery is 12 volts. Now, the total resistance here was 1.33 ohms. And we're trying to find the total current. So we use the equation I total equals V total over R total. All right? V total is 12 volts. R total 1.33 ohms. All right, let's do the math and see what we get. All right, 12 divided by 1.33, and we get, all right, about 9.02. All right, 9 points, and we've got only two significant figures, so we'll just stop at the 9. We've got 9.0 amps. Okay, so you see here that the series circuit with the same three resistors gives us a greater resistance and therefore a small current. Note that resistance and current are inversely related. So a larger resistance will give you a smaller current. Remember, we're dealing with all totals here. Notice that the parallel circuit gives you a smaller total resistance. Therefore, the current, the total current, is larger because current and resistance, according to Ohm's law, all right, R equals V over I. All right, notice that current and resistance are inversely related. You'll like these two shortcuts, two special rules for total resistance in a parallel circuit. Now remember, these rules only work for parallel circuits. Rule number 1, the total resistance is always less than the resistance of the single smallest resistor. And rule number 2, if all of the resistors are equal, then the total resistance is the resistance of one resistor divided by the number of resistors. Let me show you how this works using the problem that we just finished. Let's see how the special rules for total resistance in a parallel circuit apply to the problem that we did just a few minutes ago. So, the first rule said that the total resistance in a parallel circuit is always less than the resistance of the single smallest resistor. Now in this case, all the resistors are the same. So the single smallest resistor would be any one of the three 4 ohm resistors. So we'll just say that the single smallest resistor is 4 ohms. Now we know that we calculated, and this is according to rule number 1, we calculated that the total resistance for this parallel circuit was 1.3 ohms, all right, repeating. Now, the smallest single resistor is 4 ohms. So you see that the rule applies. The total resistance is less than one of the single smallest resistors. The total is less than 4. Now, about the second rule. And I've copied the second rule over here in equation form. The total resistance, now this is only for a parallel circuit in which all the resistors are identical. They all have the same resistance. You take the resistance of one resistor and divide by the total number of resistors. So in this case, the resistance of one resistor, I'll be working across here, the resistance of one resistor would be 4 ohms, and the total number of resistors is 3 resistors. And 4 divided by 3 gives us a total resistance of 1.3 repeating, all right, ohms. Okay, so our special rules for parallel circuits check out based upon the problem that we did just a few minutes ago. You'll like using these. Now, just remember, you can only use this one when all the resistors are identical. Now let's do a problem where the 3 resistors are not the same. So here we have a series circuit. The battery is 24.0 volts. R1 is 2.0 ohms. R2 is 4.0 ohms. R3 is 4.0 ohms. And when we do the parallel circuit, everything will be identical except for the parallel setup. R1, again, is 2 ohms. R2 is 4 ohms. And R3 is 6 ohms. Let's calculate the total resistance for the series circuit. So R total equals R1 is 2.0 ohms. R2, 4.0 ohms. R3, 6.0 ohms. Okay? So, R total, 2 plus 4 plus 6. The total resistance here is 12 ohms. Again, we've got only 2 significant figures. All right, now, we might as well, since we have the total resistance and the total voltage, let's find the total current. All right, so I total equals V total over R total. All right, the total voltage is 24 volts. The total resistance is 12 ohms. That means that the total current for this series circuit here is going to be 24 divided by 12 is going to be 2 amps. Okay? Now, parallel circuit. All right, so 1 over R total is going to be 1 over R1, which is 2 ohms, 1 over R2, which is 4 ohms, and 1 over R3, which is 6 ohms. Okay, now, 1 over R total. Okay, 1 divided by 2 is 0.5. 1 divided by 4 is 0.25. 1 divided by 6, right, should be 0.167. Okay, 0.167. Add them all up. All right, 1 over R total equals, add them all up, 0.5 plus 0.25 plus 0.167 equals 0.917. 0.917, all right, that's not ohms. That's 1 over ohms. Okay, 1 over R total equals 0.917. We're not done yet. I don't want 1 over R total, I want R total. So I'm going to switch these two and then divide to find R total. All right, so we find that R total is equal to 1 divided by 0.917. Let me fix that. 0.917. Okay, so 1 divided by 0.917 equals 1.09. All right, we've only got 2 significant figures, so R total is going to be 1.1 ohms. All right, that's your total resistance. Okay, now, let's find the total current. Now, to find the total current, I will revert back to 1.09, right, to find the total current. All right, so I total is equal to V total over R total. The total voltage, 24.0 volts. The total resistance, before I rounded it, was 1.09 ohms. 24 divided by 1.09, my total current is 22. All right, I total equals 22 amps. Okay, now, what I want you to notice, a couple things here. So, to summarize, the equations for the total resistance for a series circuit versus a parallel circuit are not the same. The series circuit is very simple. To find resistance total, you simply add up the individual resistances, R1 plus R2 plus R3, as many as there are. And you're going to get your total resistance, which in this case is 12 ohms. Right now, for the same components, the 24-volt battery, the 2, 4, and 6 ohm resistor, the parallel circuit is calculated in this way. You're getting the inverse of the total resistance by taking the inverses of the individual resistances and adding them up. So at this point, you've got the inverse of the total resistance. And the unit, all right, by the way, at this point, the unit is not ohms, it's 1 over ohms. All right, so we're obviously not done yet. All right, you need to take the inverse of that, all right, now to get your total resistance right here, which is 1.1 ohms. All right, now at this point, I simply truncated, just chopped it off at 1.09, and then rounded to 2 significant figures here for my correct final answer to the correct number of significant figures. All right, now, what I also want you to notice is that there is an inverse relationship between current and resistance. Here's Ohm's law. All right, Ohm's law, R equals V over I. All right, so you see that there is an inverse relationship between resistance and current. So when you calculate the total resistance for the series circuit, you're getting 12 ohms. When you calculate the total resistance for the series circuit, you get 12 ohms. Because the total resistance is calculated differently for a parallel circuit, you're only getting a total resistance of 1.1 ohms. This is one of the reasons why you set up a parallel circuit, to get a smaller total resistance so the circuit draws more current, right, so that you can power more devices. All right, now, notice also that for the series circuit, the total resistance is 12 ohms. The current is 2 amps. When you look at the parallel circuit, where the total resistance is lower, the total current is obviously going to be higher, 22 amps, because there is an inverse relationship between resistance and current. Again, when the total resistance drops, when the total resistance decreases, the total current increases. All right, so that's another little thing that you want to realize about this little demonstration here. Now, one final thing. The 2 special rules for parallel circuits. All right, let's take a look at those. All right, rule number 1, which is always in effect for parallel circuits. The total resistance, R total, which is 1.1 ohms in this case, is always less than the single smallest resistor. The single smallest resistor here is 2 ohms. The total resistance is less than the single smallest resistor. Now, the second special rule for parallel circuits does not apply here because the resistors are not the same.